Let's take a quick look at how we can break AES-ECB encrypted data without a key. Before we begin, I will briefly go over the basic concepts to refresh our knowledge. The Advanced Encryption Standard, also known as AES, is a symmetric encryption algorithm which is mainly used to encrypt files, images, videos, messages, packets, and a lot more. Although the implementation of the AES algorithm is quite complex, at its core, AES simply takes plaintext input and produces an encrypted ciphertext as output. Obviously, this process can be reversed to decrypt the ciphertext back into the plaintext, as long as the key is known. AES supports 3 key sizes, 128-bit, 192-bit, and 256-bit. For the purposes of today's video, we will assume that our AES algorithm uses 128-bit key size, which is 16 bytes. This means that the AES algorithm only accepts data that is exactly 16 bytes long. Okay, then what happens if we want to encrypt the data that is larger than 16 bytes? AES won't accept any data that is not 16 bytes long. Well, we can simply divide that one large chunk of data into 16-byte blocks and apply the AES algorithm to each of those blocks. Okay, then what about the case where we have the data that is not evenly divisible by 16 bytes? This is where the padding comes in. Padding is added to the end of the data to ensure that it fits perfectly into 16-byte blocks. There are many different padding schemes available, but one common approach involves adding bytes to the end of the block to fill it up to the block size, with each added byte containing the number of padding bytes. Let's take a look at these blocks again. As you can see, each block is independently encrypted with AES. This is known as electronic codebook or ECB mode. Compared to other types of block cipher modes like cipher blockchaining, ECB is considerably weaker in terms of security. One example is when you have 2 identical plain texts that are encrypted. As you can see, the encrypted ciphertexts are exactly the same. Now we're going to leverage this weakness of electronic codebook to decrypt a ciphertext without ever knowing the key. Okay, so we have this ECB Oracle CTF challenge from CryptoHack, and we have the key and flag here, and we can provide some input which will be converted into hex, and that will be prepended to the flag, and it's also padded. Interestingly, they are using ECB, and just to note that ECB uses 16 bytes. So we create the encrypted ciphertext and it will be returned back to us. Okay. Now we're going to try use the front-end UI to talk to this backend server. Let's just start by prepending some values. So let's start with 1 byte at a time. We can see that the ciphertext is there. Interesting. As you can see, the ciphertext's length is pretty much the same all the time. And at the 7th byte, the ciphertext changes. The length of it grew like significantly. So with this behavior, I guess we can try to derive the key length of the ciphertext. But before we do that, let's just play around with this encrypt function because I want to see what it's exactly doing on my local machine. Okay, we can get rid of the things that we don't need. Let's just print out the plaintext that we got. We wrap it within string, and we don't need the flag for now. It's going to be padded, and we will print the padded to just see what it looks like as well. And let's see, encrypted. we're gonna just ignore the error. And we also want to print the encrypted text. So encrypted, and we will just set a message, crypto flag. So this is just a crypto hack thing. They use the format of crypto, open bracket, something, and close bracket. So we just use this for fun. So message that encode, we return it into hex, and call the function that we just created. And let's test this function. Cipher invalid syntax. Okay, that. Oops. Okay, it's probably complaining because I used tab there. Key is not defined. Oh, I forgot to make my own key. So I just use an arbitrary A's as the key. And there we go. We have plaintext crypto flag, and you can see because this is not 16 bytes, we have 4 bytes added at the end to make it 16 bytes at the end. And we can play around with this a little bit. So let's pretend a byte in front, and we are assuming that we're gonna get less paddings because the more we prepend, the more the 16 bytes is gonna get filled. So we're gonna probably see some 3s. Yep. So 03, 03, 03, and eventually we will fill up the entire 16 bytes. And interestingly, this code actually produces entirely new block of paddings. That's why if we prepend 7 bytes of plain text to the flag, we get the larger ciphertext, while if we pretend 6 bytes of plain text to the flag, we get smaller ciphertext. So with this, actually, we can try to extract the exact length of the flag. So let's just use the UI again. Let's try to get the ciphertext of the of our input, which is 7 bytes. Let's put that into our notepad. And let's try to get it to 16 bytes. We do know that this should be just full of padding, this block. And we need to also subtract our input, which was 7 bytes, from the addition of these 2 blocks here. So there will be 16 plus 16, there will be 32 blocks, 32 bytes. We need to subtract 7 bytes that we prepended, and we get 25. So this will be the exact length of the flag. And now let's just play with the inputs a little bit more. Let's give it a lot of A's, a lot of bytes, and see what happens. So we get the ciphertext, and let's try to analyze it. Let's put it here and divide it by 16. And interestingly, you see that we get same blocks for a lot of those, a lot of A's. And because of the no pseudo randomness in the blocks, we can choose any plain text and convert it and get the corresponding ciphertext. So what we have so far is the exact length of the flag and the ability to get any ciphertext of any plain text that we want. And by chaining these 2 facts, we can actually extract the flag without ever decrypting anything. So the backend server doesn't have any decryption code, and we don't need them. So to quickly go over the exploitation steps, let's say when we have a plain text like this, so this block is 16 bytes. Let's just say we are prepending an extra byte at the front. Then what happens is that the last byte will be shifted to the next row. So it will be shifted to the next row like that. And then it will be padded with a bunch of paddings like that. And if we add another byte, then this G will be put here, and we'll have padding and so on. So because if we prepend the byte at the front, this closing bracket will be shifted to the next block, padded by 15 bytes. And we also know what the padded bytes will be. So we just have to figure out the very first byte, which is the random value. We are just assuming it is a closing bracket, but we can test our theory by checking it ourselves. So let's try to get this and also compare with our input. So let's try to put some A's and retrieve the ciphertext. So let's put 7 bytes here. Get this ciphertext, and let's try to divide it. We have this, and as you know, this will be definitely the padding of 16, because again, when we prepend 7 bytes, it will have the perfect size of 16 bytes and 16 bytes, and this will be just padding of 16s. So now we're gonna prepend one more byte. So we have 8 bytes here, and let's try to analyze it. So now this will have the value of this encrypted. So that will be the last byte of the flag and the padding of the number 15s. So the target block we're trying to compare is this EF79. Because CryptoHack always has the flag in format of something like crypto, and the last byte will be this closing bracket, we can try to create a ciphertext of this closing bracket padded with 15 bytes and see if it matches the target byte that we have here. So let's try to do our request through the endpoint here. So let's try curl. The endpoint is encrypt, and we will have to give the hex value of the closing bracket. So we see it's 7D. So we put 7D, and again we will need to fill the paddings of 0F, which is 15. So we have to put 15 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And let's try to request. It's getting redirected, and we get this ciphertext back. So let's try to analyze this as well. And in theory, because we're prepending the close bracket with a bunch of paddings, we should be getting the same result as the last block of the previous input that we have requested with. And we can definitely confirm that we have the match here, and we can say that we successfully extracted the last byte of the flag without having to decrypt anything. So this is just doing it manually, and we can easily brute force all 16 bytes by scripting it in Python. So let's go ahead and do that. So we will create the exploit.py, and first let's get the functionality of the request. So gonna put the endpoint here. Get the parameter, and we just need to get the JSON data back. And let's see if it works correctly. So let's just give it some A and see if it works. And we get A back. Oh, we're supposed to call the get request. Yeah, we get the ciphertext back, and I just don't want to see this in JSON format, so I just extract the data from the ciphertext. There we go, this should work. Nice. Now I'm gonna create a list that holds bytes from 00 to FF in string representation, and this is so that we can use those into the parameter. So let's create a list with strings from 01 to FF because we don't need a 00. So in range 6. We are gonna get the hex value and get the last two. So what this does is that if you have a hex representation of 0xAA, we just want the AA instead of the 0x at the front. So that's what it's doing. And we're gonna get the length equals 1. We're gonna add 0 at the front. And basically what it's doing is that if we have a value like A, first of all, it's gonna strip away that 0x and we just have A. But I also want to put 0 at the front, so this is what it's doing. And finally, we're just gonna add it to the bytes list that we created. And we can try to print the byte list, see if it's populated correctly. And yeah, we have 01 to FF, so that's all we need. First, let's create the payload, which is going to be the offset with the 7 bytes, and we obviously want to add one more byte into that because we want to prepend the byte so that we get the last byte of the flag shifted to the next row with a bunch of paddings. And we want the ciphertext. We use the request function, pass in the payload, and we want to get the last block. So if we get ciphertext like this, we are trying to get the last block from the ciphertext. So let's do last block, and we're gonna get the last block. So this we get the last 32 bytes of the data, and we are gonna go over all of these strings and brute force until we find the matching character. So B in byte list, we're gonna compare the very first line or block with the target, and again the target is obviously the last block, and we want to match our input block with the last block and see if they are equal or not. If they are equal, that means we have the correct byte guessed. So we're going to create an input of the byte and add 0f because that's 15, and we're going to put 15 of those paddings at the end. And we're going to get request and try to get the first block out of it, which is the first 32 bytes. And let's just print it to make the debugging easier. Testing input, and finally we want to compare the first block to the last block and see if they are equal. If they're equal, we know that we found the correct byte. and we're gonna break here. So let's try and running that. So the script started. It's brute forcing 1 byte at a time. It's looping over the byte list that we created, and if this works well, we are gonna get the 7D, which is the closing bracket. So I'm gonna pause the video now, and I'll see you guys after this script finishes running. Okay, I'm back, and here we go. We found the 7D, which is the hex representation of the closing bracket, or the closing curly bracket. So now we want to automate this process for all 16 bytes instead of just extracting the very last byte. That's the whole point of this script. So let's first refactor the code a little bit. Let's first of all create some offset, which will be the offset here, and we'll set the payload to offset, and we can just prepend A or append A every time to the payload. Let's also create a pad count, because we're not gonna be always appending pads of 15. So we are eventually gonna pad from 15 to 0. So let's start with 15, and it will eventually go down. Also, we want to keep track of the extracted bytes that we have. And finally, we also want to have a blank block. And the reason we need the blank block is because once it reaches the padding of 0, the server will produce a new padding full of blank blocks, which is this. And we will have to check the previous block and extract it that way instead of the last block, because the last block will just have nothing in it. So that's the reason we'll have to have a condition to check for that. Also, we will create a function which will return the correct padding byte for a length. So we're going to return the byte from the byte list, and this will replace right here get padding with the pad count. And instead of hard coding, we're going to have to dynamically calculate the padding, so times pad count. Alright, now we just have to create a while loop and make sure this happens 16 times, because we want to extract all 16 bytes on the last block. While length of flag is 16, actually 32, because we are using AA to represent 1 byte. We are going to continue this. We'll do this for every byte, and every time we extract something, we'll need to decrease the padding count by 1. So we'll do that. And again, for the 16th byte, we need to make sure to add the blank block check, because it's not going to have any paddings, and it's going to have a new line of padding appended to it. So we have to check the block previous to that last block. So we will check if the last block is blank block. In that case, we will just set the last block point to the block before it. And we'll reset the pad count to 16, because we are gonna have to start with 16 pads. So let's try running it. And this might take a few minutes, and let's see what we get at the end. Actually, I found a critical bug within my script where I actually don't add any byte to the flag, so it just keeps extracting without actually adding anything, even though it found the value. So we're going to stop that and actually make it so that flag has the byte that we just found prepended to it. So let's do that. Also, we will fix it here. So we are prepending the byte before the flag. And let's try running that again. Okay, we're back. It actually took quite a bit longer than what I anticipated. But we have the last byte found. So if our script ran correctly, then we should have the 16 bytes extracted. So let's go ahead and check that right now. And yeah, it looks like we have a part of the flag extracted. So let's copy that and make sure that this is actually 16 bytes. So let's put that in. And yeah, we have 16 bytes. So again, the flag's length is 25 and we need 9 more bytes to extract from. So we'll have some crypto, open bracket, and a little bit more data, and it will end with this data right here. So I'm gonna copy this because we're gonna need this to extract the rest of the data. So because we extracted last 16 bytes of the flag, now we have to recover the rest of the 9 bytes. And to do that, we simply have to edit this script a little bit so that we are now comparing the first block to the second last block. And again, the reason we are not checking the last block is because now the last block has the parts of the flag that we have already discovered. So we just modify the script a little bit. We will actually hard code the flag with the value that we found, and we'll also adjust the offset a little bit. We're gonna add 16 extra bytes there, and we're gonna also have to adjust the loop condition, and we're gonna simply add 18 because we need 9 more bytes. So 9 times 2, 18, and we will just make that to 50. Okay, now we just have to get the last block to point to the block previous to the very last block. So we'll set -64, and it will check up to the, in theory, this should produce a actual flag. So let's try to actually print out the flag. We're going to convert it from the hex. Hopefully we get the plaintext output, and we're going to run it. So yeah, it's starting off the flag that we have acquired before, and it's going to try to brute force until the end of the flag is reached, or the very first byte of the flag is reached. Our script has finished and we get the flag. This was my solution, and there are obviously more elegant ways to do this, but I just wanted to share that how I did it originally. And the final lesson here is that if we have a chosen plaintext text scenario where we can convert any plaintext into a ciphertext, and we have a server using ECB, which is non-pseudo-random encryption, we can try to extract 1 byte at a time, starting at the end of the ciphertext by using the padding attack. That was it for this video, and thank you very much for watching.